I'm Alexander Clegg, and in this section we will cover Habitat Sim Interactivity. This is a use case-driven tutorial where we'll talk about adding new objects to a scene, kinematic object manipulation, the physics simulation API, sampling valid object locations, generating a nav mesh that includes static objects, and agent embodiment with continuous control. First, we're going to install and configure some path setups, imports, and utility function. Okay, so included in this are some ways to make the configuration easier. If you saw the Sim Basics tutorial, then you'll understand where some of this stuff is coming from. If not, I suggest you check it out. We have a simple function for creating default settings and making the sim global object directly. We're also defining these template managers. We'll talk about what these do later, but essentially any object, scene, or primitive that you want to add to the world or use can be configured in the template manager before instancing. This allows you to do domain randomization and configure specific physical properties programmatically before you instance an object. All right. We're also going to define a couple of simulation utilities here, including sample object state, which we'll come back to in a bit. Okay, having done that, let's load the simulator in the scene, now made very easy by getting the default settings and making a simulator from those settings. And we'll just do this every time we want to reload a scene for this tutorial. So we're going to have 4 use case-driven subsections here. First, an introduction to interactivity, then physical reasoning tasks, followed by generating scene clutter on the nav mesh, and finally, continuous embodied navigation. For more details about what I cover here, you can check out the interactive rigid objects tutorial, which is also available in Colab. So let's jump right in. Here we're just going to add an object and simulate. First, we're going to create a drop-down so we can select which object we want to add based on our template manager. Then I'll just run this cell. And what this is going to do is it's going to add whatever object we've selected from the dropdown, set its offset and orientation from this configuration over on the right. And this is all local to the agent. So we have a utility function to handle that, set object state from the agent using the configured offset and rotation. The rotation we define here will be Euler angles. So we'll compose those and then set them here. Then we simply simulate and create a video. So here you can see we've added this object to the scene. And here's an image of what that looks like. Before we simulate, you hit the button, we run physics simulation, and produce a video of these frames at 60 Hertz. Now, let's talk about some physical reasoning tasks using this kind of functionality. So let's say you have an agent that is holding a fixed camera position to collect data so that your model can do classification of physicality or prediction of things like trajectories. So we're going to reload this object GUI again. And then I'll just run the first script here. Once again, we're just dropping an object from a scripted location. If we toggle the kinematic switch, now the object is dropping at a constant rate. And this is a non-physical motion, right? Because we don't expect an object to drop with no acceleration. So presumably your classifier would be able to tell that one of these is physical and one is not, given the ground truth. And you're just kind of generating data for that classifier. Once again, all we have to do here is add the object from the handle. And here we're getting this handle from that dropdown. This add object by handle function takes that handle and actually prints that object or instance it into the scene, and then gives us an object ID. And this object ID can be used then to reference the object in the simulator from then on. So using this utility function to set the object state from the agent again, we pass in that object ID, give an offset, give an orientation. In this case, we're using a random quaternion from our utility library. So we're just randomly orienting that object. And then we're doing the simulation to get the observations and making a video. Now, if the scenario is kinematic, so let's run that again. What we're doing is we're setting the object's motion type to kinematic using that object ID. We're getting that object's velocity control structure, setting the linear velocity to be controlled, and then setting that to be the gravity direction at 1 unit per second. and that's going to produce this. So inside of simulation, these velocity control structures for kinematic objects will be integrated automatically and applied. So that's what's happening here. We clean up by removing all objects. Now let's look at an object permanence example. Here you might be training a classifier to predict whether this example is demonstrating object permanence or not. Is there something disappearing when you predict that it shouldn't be? So we're going to add two objects to the world from the same handle. So this is printing two instances of this template into the world. We're setting both of those to different states relative to the agent. We're grabbing the template manager, and we're looking for a template that has the cube substring and the first one of those. So if we go back up here and we look at what's in this list of templates, that's going to grab the cube solid first. So that's what we're doing. This is a substring query to get a list of all the templates in our object manager, our template manager, that have the cube substring, and then we're going to grab one of those, and that's the handle. We're then going to get a copy of that template from the manager, scale it, and that's producing this occlusion surface. We're stretching that cube out and then placing it into the scene. We do so by re-registering this as the occluder cube object, adding it to the scene by that handle, and then setting it to kinematic and setting its state. Notice that if we go up here and we look into the primitive-based object template handles, if we rerun this, the occluder cube is now there. So this has been created and it's in our template library. So it'll show up in these dropdowns. All right. Then we're just going to simulate for 2 seconds. And every time we simulate, every time we pass a 60th of a second of stepping the simulator, we're going to ask, if this object exists, is its translation lower than the occluder cube center of mass? So we're checking the y component of both of these. If so, we remove it from the scene. So this is how we're doing the actual object removal here. Great. Now let's talk about maybe another physical plausibility classification. Here with an invisible surface. So this object is being dropped on the couch, and you would expect it to roll off onto the couch. Instead, we've introduced an invisible surface. We can rerun this without the invisible surface, and it rolls the way you would expect. So how do we do that? We're adding the object as normal. So we're querying a template handle for this UV sphere solid. We're adding that object by handle. We're setting the state. Then if we're introducing the surface, we're going to do the same thing we did for that occluder cube surface previously. We're going to grab the template. We're going to scale it. This time we're setting visibility. If we set the visibility to true, so this is the default, then it'll add that object and you can actually see it in the scene. So here, this is the surface that the object is actually rolling on. If we set this to false, then it does not produce a render object in the actual scene, and it only produces a collision object. Then we register that template as the invisible surface. We use that handle to add it to the scene. We set that state relative to the agent, and then we set the motion type here to static. Now, we're going to simulate for 3 seconds and make the video, and that's what we're seeing down here. Let's try a trajectory prediction example. So in this task, we have this counter surface. We're specifying a bounding box on this surface and generating a bunch of targets automatically inside of that bounding box. We're grabbing a sphere, adding it to the world at the agent's location, and providing an initial velocity to toss it at the targets. And let's see how this works. First, we're going to seed the world, so you can try different seeds for that random number generator for the targets. If we show the target zone, so you can see the bounding box that we're actually generating this from, you can see it down there. It is physical, so we don't want to leave that around, so we're going to remove it again. We're going to set the agent state to somewhere that we know is the correct place in the scene, so we've pre-picked this location. You can do that by opening up Blender or using the script that we used in the NavMesh tutorial from SimBasics to place the agent. Now we can load the target object. We're going to use this Cheez-It box. We define this bounding box, which is a range 3D object, and this is an axis-aligned bounding box. For each target, we're going to add that thing to the world. We're going to rotate it so that it's not on its side anymore, because the default cheese-a-box is on its side. And then we're going to use this sample function to find a valid placement for that object in the world. And I'll talk more about this in the next example, where we also generate sampled places from the nav mesh. So for now, this is just going to sample from the bounding box and guarantee that there's no object colliding with the one we're trying to place. If we want to show that target zone, we're going to do the same thing we did with the occluder cube. Grab the template, call it, change its scale here, call it the target zone and re-register it, and then add it to the world and set it as motion type static, so we're not going to move it. Then we're going to grab the sphere, and we're going to make a copy of its template, and here we're going to generate a new mass for that template, so we're configuring a physical property. And you can configure that property here on the slider, and then we're going to register that template, add it to the world, and set the object state from the agent state. Then you're going to be able to set the linear and angular velocity of that object. This is the initial linear and angular velocity of the ball. So when we add it to the world, that's what the first frame's velocity is going to be. After that, it will be overridden by simulation. So let's try something. Let's turn down the ball's mass, something very small. And you'll notice here that as we fling it, it's not going to affect these boxes at all. If we turn it up to really big instead, so it's a really heavy ball, now you see it's flinging those objects across the room. So now it's like throwing a bowling ball. So go ahead and play with this, play with the seeds, generate different object configurations, and you'll be able to maybe train a model to predict what will happen in the scene given the initial conditions. So let's talk about generating scene clutter on the nav mesh now. So in this example, we'll use the nav mesh to place objects on the surfaces. And then once they're placed, we'll set them to static. And then we will, and essentially what setting them to static will do is disable their ability to be kinematically or dynamically manipulated. Once we have a static object, we can recompute the nav mesh, including those static object meshes in the voxelization. And that's going to add them as navigability constraints. So first, we're going to load a new simulator scene. This time we're in the apartment again from the previous examples. We're going to regenerate this GUI. And then we're going to run the script to place these objects in the world. So here we're placing a banana, and you can see the nav mesh is being computed around that banana. Let's do it for cheez-it boxes. Do the same thing. And here now we're creating these giant cheez-it boxes that are blocking off doorways. The agent can no longer get past them. So let's talk about how we do this. We're positioning the agent in a specified location after we seed the world. We're specifying the scale of the object and the number of objects we want, and you can play with that over here if you would like to. We're using the template manager to scale up the object. Then we are setting the visualization for the nav mesh to true. And we're adding all of these objects again using this sample object utility. So now is probably the right time to go talk about what's actually happening there. So here we've defined this sample object state utility. We're going to have a couple of qualifiers coming in. We can't do anything with a static object because we can't move it. We're going to move it to have to test its location. If we're going from the nav mesh, we need to make sure it's actually loaded. Otherwise, we have to pass in a bounding box. Those are the options we'll provide. Then we're going to go through for a fixed number of trials. We're going to try a certain number of times to find a valid placement. If we're sampling from the nav mesh, we'll use the getRandomNavigablePoint method. Otherwise, we'll just grab a random location inside of the bounding box. We'll set the translation of that object to the sampled location. And then we'll set the orientation of that object, either only manipulating orientation around the y-axis, if we want the object to stay in a certain up orientation, and setting that rotation through the simulator API for the object, or using a random quaternion. Then we'll elevate that object off of the nav mesh before we check whether it's colliding with anything. And this is just to guarantee that we aren't going to be putting the object inside of the floor, for example. So we can grab the object scene node. From that, we can get the object's cumulative bounding box. This is an axis-around bounding box in the object's local frame. So we'll transform it into the global frame with the object's transformation. Then we'll push that object off of the nav mesh by half of its Y size bounding box and the scene collision margin. And we grab that up here from the scene template manager. And the first entry, whenever you load a fresh scene by closing the simulator, will be the scene that you've loaded. So we can grab the margin property off of that. And this is just to guarantee that when we do this contact test down here, we aren't accidentally infringing upon the collision margin, which is used for simulation stability. So we'll set that translation to push things off, and then we'll do a contact test. This will return true if that object is in contact with any other object in the scene or with the scene mesh itself. Otherwise, it will return false. Then we know we have a valid placement, and we can move on. Okay, so we did that here to generate these cheese box locations in this bounding box, and that's why none of them are colliding. We can also do it here to position these cheese boxes on the nav mesh and then recompute it. Once you've got those objects placed, you just need to set them to static, and then you can recompute the nav mesh using just default properties or whatever properties you want. And then you just set the include static objects flag to true on the recompute, and it will consider those meshes in the voxelization. Then we just produce a video for visualization, and here we are. So for the last example in this tutorial, we're going to talk about embodied continuous navigation. So we're going to do an embodied navigation interaction scenario where we have an object and an agent, which is embodied by a rigid locobot mesh, placed randomly off of the nav mesh. We're then going to compute a path for the agent to reach the object and execute that with continuous path following control. The object will then be gripped by the agent, and a second path, which we compute, will be used for the agent to reach the goal location. The gripped object will then be released, and we'll throw it in front of the agent. If you want a refresher on some of this nav mesh stuff, go ahead and look at the SimBasics tutorial again. I'm going to gloss over some of that, assuming that you can go there and look for it. So first, we're going to regenerate this GUI. We're going to load some utility functions, and I'm going to start by just running this example so it starts to produce the video, and we'll talk about what these supporting utilities are. We have a continuous path follower, which is just going to take in a path that we provide and a simulator and an agent, and we're going to produce this set of point segments and tangents, which we'll use to then later compute positions continuously along that path. We'll also be able to update a waypoint by pushing it away from the agent's location. So as the agent gets close to that waypoint, it'll move farther away along the path. And that's what's being done here. We have a function to set up a path visualization so we can see what this path actually looks like. And I'll show you that in a second. We also have a function here to track the waypoint, and this is where the actual continual control is happening. So we have some maximum turn speeds and linear speeds, and we're just finding the angular error between the waypoint and the agent's heading, and using that to decide whether we're going to be moving forward or not, and at what speed, and then whether we're going to be rotating or not, and in which direction, and at what speed. And then we're using a passed-in velocity control structure to actually do the control. So we're just setting those things into the velocity control structure, and then we'll integrate that manually inside the loop. We'll define an object gripper class, which is just very simply syncing the state of any object with the agent state. We define an offset for the end effector for that to make it consistent. It also defines a function to grip the object initially, which just sets it to kinematic, and then sets the initial state of that object. And a release, which is going to set the object back to dynamic, and then apply a linear velocity to toss it. So this is just a utility to simplify the actual script. So what does it look like? Here we have this agent. You can see it's following this waypoint that's being produced along the path into the bathroom, where for some reason there's a banana in this shower stall. Fancy that. Then we're going to follow the path back to some location next to the bed and toss that banana onto the floor. Great. So let's see how this is actually happening. And I'll note here that you can change the seeds to get different paths and look at cool other ways to do this. And you can also change the object here if you want to do something other than a banana. So play around, should be pretty fun. You can turn the waypoint indicators on and off, and you can actually configure sliding on or off. Note that if you turn sliding off, it is possible, due to the smoothing applied by this continuous controller, that you'll collide with some corner and get stuck. So just beware of that. So what's actually happening here? We're setting up the settings for our simulator. We're making the simulator for that. We're really just turning on several new observation modes and configuring the height of those sensors to be the same height as our robot. So here, that robot camera that you see down here is where we're putting the first-person views that are overlaid in this visualization. Okay. Then we are going to do this seeding, and we're going to compute an inflated nav mesh so that the agent doesn't edge the corners too severely. Now we're going to add the agent and the object to the world and set the agent to be kinematic. An important note here is that when we're adding the agent to the world, we'll need to add it with the agent's scene node supplied as an attachment node for this add object by handle function. When you do that, we'll actually be attaching the object directly to the current agent's scene node where the sensors are attached. When you want to remove that agent object from the scene, you should very explicitly delete object node false in that remove object function. What this is going to do is it's going to prevent the simulator from actually destroying the agent's scene node. If you don't do this, the agent's scene node will be destroyed, and you can get issues trying to query sensors later. Now, if you close the simulator and reopen it, then you don't have to worry about this. But if you're going to continue using the same simulator and you want to remove an object embodiment of an agent, be sure to do this. Okay. We'll set up the velocity control structure. This is unattached to the object, so we're going to integrate it manually like we did in the nav mesh example from SimBasics. And then we're going to set that location off of the nav mesh for the agent. Great. Now we're going to actually find these paths between our various locations. So we're going to sample a location for the object we're retrieving using that sample object state function we just talked about. We're going to then configure two paths, one from agent to object and one from object to endpoint. Then we're going to find those two paths, and we'll just iterate on this until we succeed. Why do we need to do this? It's possible that on this nav mesh, there'll be multiple islands. And if you try and find a path between two islands, you won't be able to find that path. You'll get infinite path lengths. So we need to actually iterate on this until we find valid paths. Okay. Then we're going to recompute the nav mesh again using the default settings. So we're going to deflate the nav mesh and then actually run the execution on that. We're going to build our gripper and our continuous path follower objects that we talked about before. We're going to configure whether to show waypoint indicators or not. Let's turn that off and rerun this thing so you can see what that looks like. Then we are going to run the actual scenarios here. So we're going to do two iterations, one for agent to object and one for object to endpoint. After the first version, once the agent has gotten to the object, we're going to actually grip that object and set up the continuous path follower to use the second path. For both of these, we're going to do the same continuous control. If we're showing the waypoint indicators, we'll update those. Otherwise, we're going to go through a loop trying to follow that path. We have a maximum time of 30 seconds in case we get stuck here. Essentially, what we're doing is we're saying, if the time in the simulator is less than this limit, and we haven't reached the end of our path yet, keep trying. The first thing we do is update our waypoint. This pushes the waypoint away from the agent's current location. Then we update the indicators. At that point, we get the object state from the ID for that locobot. And then we do the continuous control with this track waypoint. And this is going to update the velocity control structure. We then integrate the transform to get the target rigid state. Similarly to how we did in the SimBasics NavMesh tutorial, we're going to apply the step filter to enforce navigability constraints, set the state to the agent, and then check for collisions. We don't do anything with this, but you could do something, either render a frame that shows you collided or penalize your model, whatever you want to do. Then you can sync the gripper states. This won't do anything if there's nothing gripped, or it will kinematically move the object to be updated to the agent's position if the object is gripped. Then we actually run physics for the certain time step we're at, and our time step here we're using is 1/30th of a second. Great. Then we're going to render the observation, and at the end of this whole loop, once we've hit the last frame, we release the object and simulate for 2 more seconds to throw it and show it being thrown. At that point, we make our video, and that's when we get this nice visualization you see here. So here we're showing it without the waypoints. And note that we have these nice overlays of a color, depth, and semantic image from the perspective of the agent, so at this agent's camera location. And we overlay this on to the third-person image that we're showing using our video utility. You can set that up with this list of dictionaries for the overlay settings, where you define which sensor the overlay is going to be, what type it is. It can be color, depth, or semantic. Define its image position, so we're stacking them here. Define its dimensions, and we're saying that all of these are going to be 1/5 of their original dimensions. And then defining a border width individually for each overlay. You can actually define border color too, but we're here using the default gray. Then we just pass in that overlay settings to the video utility and make the video. And at the end, we remove our objects. And so here we have this video that we're displaying. I hope you'll join me also for the advanced features tutorial, where we'll talk about some more handy utilities in Habitat Sim, and we'll talk more in depth about object templates and templates in general, which may be useful for you. So thank you for joining me here for Interactivity, and hopefully this answered some of your questions.